Hello chemistry students, in this video we'll be covering dot points 1.2.2 as well as 4, and we'll be looking at electron orbitals and energy levels. First off, maybe from the junior years you would have talked about electron shells in some capacity. Essentially, each shell houses electrons and that's where the electrons belong. And in every single shell, there is a limit to the number of electrons that you can put in there. So you'll see that in this first inner shell, we can only fit, or there are only 2 spots for 2 electrons. And then in our second shell, there are 8 spots for 8 electrons. And in our third shell, there are 18 spots for our electrons. And that sort of is shown here as we start moving through the periodic table. Our first element, hydrogen, has 1 proton and 1 electron. Our second element, helium, has 2 protons and 2 electrons. And our third element, lithium, has 3 protons and 3 electrons. But that third electron ends up having to go on our second shell because the first one is full. To continue with that, if we start looking at some larger elements, we'll see that fluorine has 2 electrons on the inner shell. And in the second shell, there are 7 electrons. Neon has 2 electrons in the inner shell and 8 on the outer shell, and we would say that it's full, it's reached its limit, meaning that sodium, which has an additional electron to that, has to put its final electron in that third shell here. We may even write an electron configuration like we can see down the bottom. So for silicon, its electron configuration is 2, or 2 electrons in the first shell, 8 for the electrons in the second shell, and 4 electrons all the way around that have been the leftovers that have to go into that third shell. You may have seen a pattern like this, which shows the maximum number of electrons which can be present in any shell. However, that's not the entire story, and this image may look a little bit confronting, but I promise that we'll only be focusing on the most important parts and pick apart the bits that are going to be the most imperative to us. We're not going to be looking at everything that I've put in front of us. But what we actually know is that we don't follow a shell principle like the one that we've originally taught you. The situation's actually a little bit more complicated than that. What we have are different kinds of orbitals. There are S orbitals like this red one here, P orbitals like the ones in yellow and orange, D orbitals which are our blue ones, and F orbitals which are colored in green. Now, these bubbles that we see represent nodes, and these show where the electrons can exist. So if we have something in an S orbital, it's kind of like one of our shells that we talked about before. This is an area where electrons can go and exist. In our P orbitals here, this is where electrons can go and exist. In our D orbitals, these are spaces where electrons can exist, and same for our F orbitals too. But there's one particular rule. 2 electrons can fit into every single orbital. So for example, if I had an S orbital like this, I could only put 2 electrons in this space. If I had P orbitals, I could only put 2 electrons in this one, 2 electrons in this one, 2 electrons in this one. Same goes for D and F as well. So here 5 pairs of electrons, and for F there are 7 pairs of electrons, 7 places to put a pair of electrons. First off, I want to look at S and P orbitals, and these will be the most important to us, and they'll be the ones that we probably will be looking at most when we move into other course content. Now, first off, S orbitals are circular in shape, and they are centered around this middle point, which would be the nucleus of the atom. We also have P orbitals here, and again, centered around this middle part, which again would be the nucleus of our atoms. They're made of 2 different lobes, or maybe we might even use the term node. Now, these nodes, again, can hold electrons, and this is the area where the electrons can be. Essentially, as it says there, more nodes, higher energy. I'll come back to this energy concept in a minute, but for this S orbital here, again, it holds 2 electrons. This px orbital runs in the x direction. It holds 2 electrons. The py orbital here runs perpendicular to the px orbital and can hold 2 electrons, and the pz orbital runs perpendicular to px and py and can hold 2 electrons. D orbitals are a little bit more complicated. Again, they hold 2 electrons each, and the image that you see in front of you, the shape that you see, is where those electrons can be. Now, these ones are designed with all sorts of interesting three-dimensional mathematics and algebra and all sorts of stuff. We don't really need to know how they're formed, but note that they are different sets of four lobes, these ones on the outside, and none of them overlap over the top of each other. If we were to put them all together, there'd be lobes pointing in all different directions and it would all be symmetrical. This DZ squared one is a little bit more interesting and sort of runs through the middle of them all and has this donut ring shape as well. We don't need to worry too much about them all that much. Certainly not the shape of them or why they exist. Now, something interesting is that the patterns of all of these orbitals fit the patterns of our periodic table. Now, our periodic table is made and constructed for lots of different reasons and means that all of the elements share all of these interesting patterns. But in particular, what we'll notice is that our s orbital only had one kind of node. It was a single circle. And that it held two electrons. And what we'll see, and this will make a little bit more sense in the second video, but there is this S block here that contains two columns, one column for each of the electrons that fit. For our p orbitals, we had px, py, and pz orbitals, all of which could hold two electrons, meaning that if all of them had electrons in them, the px, the py, and the pz, in total there would be 6 electrons in total, which makes up this p block here, which is on the right hand side of the periodic table. There are 6 columns for 6 electrons. We also have our d block, which is in the middle, also known as our transition metals. Now there were 5 different orbitals, which meant there were 5 pairs of electrons. Now again, 5 pairs of electrons, that's 10 electrons in total. One column for all 10 columns, for all 10 electrons that we have here in this D block. And our final one down the bottom, and this is the one that we will talk about by far the least, but our F block here is made of 14 columns for 14 electrons, which makes sense because, as we looked back before, for our green F block, there was 7 different kinds of orbitals, each which could house an electron pair. Something else to note, which will make a little bit more sense when we do one of our practicals, is that each of these orbitals have a different energy level. Our 1s and 2s in particular are our lowest energy levels, followed by 2p, which if we look back at our periodic table, runs in order, so 1s, 2s, 2p, if we were to go in ascending order of atomic number in our periodic table. We'll notice that after 2p there is 3s, 3p, and 4s, which is what we see here, that 3s, 3p, and 4s all ascend in energy as well. And what I will tell you now is that this pattern continues as we move up energy levels in a diagram like this. So what we can conclude is that the electrons that belong in the 1s orbital have the lowest energy. And that's actually the reason why we would put electrons in that 1s orbital first. We would then put electrons in the 2s orbital, the 2p orbital, the 3s orbital. That will make a little bit more sense in the coming video though, and certainly will be something that we practice in class. And with that, I'll leave it there. Now our next video, just to sort of break everything up, we'll be focusing on electron configuration. So essentially what that means is we'll be putting electrons into those orbitals that we saw before, similar to what you would have done with simple electron configurations in years 7 to 10. Until then, catch ya.